Somewhere within this extraordinary image, there are planets that no one has discovered yet. Not just 1 or 10, but perhaps hundreds or even thousands. Hidden among more than 60 million stars, buried beneath glowing clouds of dust and the overwhelming crowding of the Milky Way's central bulge, the Euclid Space Telescope has captured something that looks like a work of art but functions as a powerful scientific tool. At first glance, the image is breathtaking, a glittering window into the crowded heart of our galaxy. The stars are packed so tightly together that the scene almost stops looking like space and begins to resemble a sea of fire. Nebulae glow through dense clouds of dust, star clusters hide deep in the background, and the field is so crowded that even sophisticated image processing software struggled to interpret everything it was seeing. Yet this is far more than a beautiful photograph. It is a reference image, a snapshot in time that future astronomers will use to discover planets as they briefly reveal themselves through the effects of gravity. Near the center of the Milky Way, stars are packed so densely that every so often, one star passes almost perfectly in front of another. When this happens, the gravity of the foreground star bends and magnifies the light from the background star, acting like a natural cosmic lens. If the foreground star happens to host a planet, that planet leaves behind a tiny spike in the light curve, a subtle distortion, a hidden signature that reveals its presence even though the planet itself is never directly seen. Euclid has not simply photographed the center of the Milky Way. It may have created the map that will allow astronomers to uncover countless invisible worlds hidden within it. Euclid was not primarily designed to observe the brilliant center of our galaxy. Its main mission is much broader and much darker. Built to study the dark universe, Euclid's primary goal is to map billions of distant galaxies and help scientists understand the nature of dark matter, dark energy, and the large-scale structure of the cosmos. Under normal circumstances, it observes deep, relatively dark regions of the sky, where its highly sensitive instruments can detect faint galaxies without being overwhelmed by bright nearby stars. For this observation, however, Euclid did something unusual. It turned toward one of the brightest and most crowded regions in the sky, the galactic bulge, the densely packed inner core of the Milky Way. This is among the most challenging places for any telescope to observe because the enormous concentration of stars can easily overwhelm instruments designed for extreme precision. Yet that very difficulty is precisely what makes the region so scientifically valuable. If astronomers want to discover planets through a technique known as gravitational microlensing, they need an immense number of stars. Microlensing depends on rare chance alignments. A foreground star must pass almost perfectly in front of a more distant background star. When this occurs, the gravity of the closest star bends and magnifies the background star's light, creating a smooth, bell-shaped brightening that may last for several weeks. If the foreground star possesses a planet, the planet's gravity introduces an additional, much smaller distortion into the light curve, a brief spike that reveals the presence of an otherwise invisible world. These alignments are exceptionally rare across most regions of the sky. Near the center of the Milky Way, however, the enormous density of stars dramatically increases the likelihood of observing such events. That is why Euclid's image is so significant. It is not merely a spectacular portrait of the galactic center. It is an enormous hunting ground containing more than 60 million stars, recorded with such extraordinary precision that future changes in brightness and position can be compared against this initial observation. In effect, Euclid has provided astronomers with a baseline, a still image captured before the galaxy begins revealing its hidden planetary systems. Most people are familiar with the transit method of discovering exoplanets. In this technique, a planet passes in front of its host star, causing the star's brightness to decrease slightly. By carefully measuring that tiny dip in brightness, astronomers can infer the planet's existence. It is an elegant and highly successful method, but it has important limitations. The planet's orbit must align almost perfectly with our line of sight, and the method works best for planets orbiting close to their stars, where repeated transits occur frequently. Gravitational microlensing works in an entirely different way. It does not require a planet to cross in front of its own star, nor does it rely on repeated transits. In fact, it does not even depend on detecting the planet's own light. Instead, it relies solely on gravity. As a foreground star passes across the line of sight to a more distant background star, its gravity warps the surrounding fabric of spacetime. The background star's light bends around the foreground star, temporarily making the distant star appear brighter. This brightening follows a predictable pattern. However, if the foreground star hosts a planet, the planet's gravity creates an additional disturbance, a small but detectable spike in the light curve that briefly betrays the existence of a planet that would otherwise remain completely invisible. This makes gravitational microlensing an exceptionally powerful method for discovering exoplanets. It can detect cold planets orbiting far from their stars, worlds located at distances where transit searches become much less effective. It can reveal planets far too faint to be directly imaged and uncover planetary systems that would otherwise remain hidden within the densely populated star fields of our galaxy. There is, however, one important challenge. To properly interpret a microlensing event, astronomers must know exactly what the region looked like before the alignment occurred. They need a precise baseline that records the positions, brightness, and separations of the stars before gravity briefly transforms the scene. That is exactly what Euclid has now provided.